Alright everyone, and welcome back to the AI Research Roundup. I am your host, Alex. Today, we're diving into a paper that's getting a lot of attention, titled Learning Compact Vision Tokens for Efficient Large Multimodal Models. So, the big challenge with large multimodal models is that they're computationally expensive. A major reason is they have to process long sequences of vision tokens, which are basically how the model breaks an image down into digestible pieces. This paper proposes a method called Spatial Token Fusion to merge tokens that are spatially next to each other, making the sequence much shorter. To ensure no important details are lost, they also introduce a multi-block token fusion module. And for those of you who want to try this out yourselves, it's great to see they also released the official implementation for this work. So in the repository, you'll find everything to get going, including detailed instructions, shell scripts for both training and evaluation on all those benchmarks, and of course, links to download the final model weights. It really is a complete package for anyone looking to replicate their findings. Okay, so let's dig into the results, because this is where it gets really interesting. This first figure is a radar chart comparing performance across several different benchmarks. You can see 3 lines here. The blue line is the standard LLaVA 1.5 model, using 100% of the vision tokens. The orange line is a simple average pooling method, and the green line is the author's new method, both using only 25% of the tokens. What's incredible is that the green line, their method, is nearly identical to, and sometimes even better than, the blue baseline. This result powerfully demonstrates their core idea that most vision tokens are spatially redundant. Alright, so this next diagram gives us a look under the hood at how they actually pull this off. The architecture introduces 2 key modules. First, an image goes into the vision transformer, but instead of just taking the final output, the multi-block token fusion module grabs tokens from several different layers. This captures what they call multi-granularity features, which is basically a richer mix of both fine details and high-level concepts. Then, those enhanced tokens are fed into the Spatial Token Fusion module. This is where the main compression happens, using a convolution to aggregate a small grid of neighboring tokens into one single, compact token, which is what shortens the sequence that finally goes to the large language model. Now, this table gives us a more detailed look at the numbers. It compares their method, which they call STC, against the LLaVA 1.5 baseline and other efficient models. The columns show performance on 8 different vision language benchmarks, and on the left, the computational cost measured in TFLOPs. TFLOPs, or tera floating point operations per second, is a measure of how much compute a model needs, so a lower number is way more efficient. And the results are striking. Their STC method runs at just 1.9 teraflops, compared to 7.6 for the original LLaVA. Despite this huge efficiency gain, its average performance of 66.3% is actually on par with, or even slightly better than, the baselines. So the numbers are impressive, but what does this improved efficiency and performance look like in the real world? This next figure gives us some great case studies. It shows 5 different examples where both the original LLaVA 1.5 model and the author's new method were asked the same question about an image. For instance, in one example, the models are asked to read text on a cake. The baseline model makes up a word, but their model reads it perfectly. In another, their model correctly reads values from a bar chart and counts cows more accurately, all while using 75% fewer vision tokens. This really suggests that their fusion method helps the model focus on the important details. These examples really drive the point home. The key takeaway for me is that we can achieve incredible efficiency not just by throwing more compute at a problem, but through smarter architecture. By learning to create these compact vision tokens, the researchers have shown it's possible to drastically cut down on computational costs without losing, and in some cases even improving, the model's ability to understand the world. This is a huge step for making these powerful, large, multimodal models practical. That's all for this week's AI Research Roundup. Thanks for tuning in, and I'm your host, Alex.